record. Okay, so we're going to talk about 4 or 5, the dynamics of rotational motion. So let's take some good notes here. And as you can tell, I have been uploading all the videos. I've been pretty consistent about doing that. So if you ever need to rewatch anything, or if that helps you study for a test, that could be a good idea. And I tried labeling by like, you know, like this is the first part of the class, second part of the class. I could probably label them better than that, but you can always kind of fast forward and see what you need. So Newton's second law of rotation is very similar to the second law of motion. Remember, Newton's second law of motion was F equals ma. So it's going to be kind of similar here. So remember, the tau, that's like force. I mean, of course, it's torque. Actually, I probably should write like this. The I is inertia. Which is kind of like mass. And the alpha is angular acceleration, which is like linear acceleration. Alpha is going to be in radians per second squared. I is called the moment of inertia of a particle or an object. And that's the formula we use for that. It's mass times radius squared. So we're squaring the radius. So that does impact our units quite a bit. If we do think about it, remember torque. What was torque, right? Torque was force times distance. Force we know is kilograms times meters per second squared. And the D was like your lever arm. That's also meters. So you want getting kilograms times meters squared per second squared. Well, moment of inertia is a kilogram times meter squared. Radians is kind of unitless in a way, and you divide by second squared. So it all kind of works itself out with the units. The moment of inertia measures how much an object wants to keep rotating or not rotating. So like to resist rotating. We tend to use calculus, which obviously we're not going to do in this class, to find this right here. Unit is kilogram times meter squared, which I just showed right here. Let me erase some of this stuff because it's a little distracting. So if you look at all the different inertia values, like here you have like a hoop around cylinder axis, which is I equals mr squared. Here you have a solid cylinder. Here you have a thin rod that's perpendicular to the length. So this is the axis right here, which is perpendicular to the length. Here, obviously the axis is parallel to the solid. Here, again, it's perpendicular, but it's not thin necessarily. Here's a thin rod, and it's at the end. Here you have spheres. And again, they do use calculus to kind of determine the exact formulas. We're not going to get into that because that's just way too much for this class. But if you do take calculus with me, then I'll show you how. If I do teach AP calculus, I'll be doing that next year. Anyway, let's keep moving here. So work for rotation. Remember, work is like energy. So it's like your force times distance, or in this case, our torque times our angular displacement. So that's going to be work, is a torque and that's going to be our angular displacement. Kinetic energy, which you saw in the Google form, so I'm going to put that up, is 1/2 I times omega squared. So this is a capital W for work. This is omega, so don't confuse those. That's actually a Greek alphabet, and it's kind of lowercase. Remember, that's angular velocity. Conservation of mechanical energy still applies to rotational motion. The initial potential energy plus the initial kinetic energy equals the final potential energy plus the final kinetic energy. Remember that KE, the kinetic energy, can include both translational, which is going to be 1/2 mv squared, which we did week 3, and rotational. It could be a combination of the two, which of course that's 1/2 I omega squared. So those are the formulas we'll be working with. And again, depending on what object and where the axis of rotation is, the moment of inertia will be calculated differently. And so this will be a great reference for you guys to have. You'll definitely want to refer to this. All right. So let's look at 2 examples. And then I'll have you guys go out to breakout rooms to do some problems. And I see there's 10 actual quantitative problems. So I figure, well, I'll probably do 1 example right now. Let me just kind of take a quick look what they're asking us to do here. How long? Or maybe we'll just do both of these. We'll do both of these, and I'll have you guys go to breakout rooms after that. Okay. So let's get down to over here. So Zorch, an arch enemy of Superman, decides to slow down the Earth's rotation to once per 28 hours by exerting an opposing force at and parallel to the equator. Okay. So obviously we rotate every 24 hours, right? But this villain is going to slow down the rotation of the Earth. Okay. Superman's not immediately concerned because he knows Zorch can only exert a force of 4. That should be times 10 to the 7th, by the way. That's a typo. A little greater than center V rocket's thrust. I don't know what that, center 5, I don't know what that is. But anyway, how long must Zorch push with this force to accomplish his goal? This period gives Superman time to devote to other villains. Okay. I can see the practicality if you're in the comic books of this word problem. Anyway, so first off, let's take a look at his, what are the things that we know? We know the force is 4 times 10 to the 7th newtons. And we are dealing with the Earth, mind you. So RE stands for radius of Earth. And you can probably just do a quick Google search on that. But I'll tell you right now, 6.38 times 10 to the 6 meters. And we also know the mass of the Earth. Okay, you can do a quick Google search there. 5.98 times 10 to the 24 kilograms. Okay. So again, we're trying to figure out how much time this person has to apply this force to actually get the Earth's rotation to slow down by that much. So one thing you have to realize is that we have omega 0, omega. Also, we're going to be dealing with, hold on a sec here. Acceleration. So we're gonna, these are gonna be like our known values, I suppose. And we want time. And what's missing is theta or angular displacement. We don't really care for that. Now, do I know the initial angular speed? Of course I do. It's 1 revolution in 24 hours. That's the initial speed of the planet Earth. If I were to put something like this on a test, I think I would break it down by parts. I think I'd say, what's the initial speed of Earth? 1 revolution per 24 hours. And let's convert that. We're going to convert that to rads per second, just a second. No pun intended, but anyway. The final velocity will be 1 revolution for every 28 hours. So we'll need to convert that also to rads per second. Now, the angular acceleration alpha, we're going to be able to get that from our torque equation. We'll come to that in just a little bit. That's going to take a little while to work out. But let's convert our omega 0 and our omega. Omega 0 is 1 revolution per 24 hours. And remember, for every hour, you have 3,600 seconds. And also remember that 1 revolution is 2 pi radians. So we'll be able to get that angular velocity in just a little bit. And same thing here, 1 hour, 3,600 seconds, 2 pi radians in 1 revolution. So you'll need to use a calculator to work this out because the numbers are pretty wacky. If you do it carefully, you should get, I think, 7.272 times 10 to the negative 5th power. Again, the units are rads per second. Over here, you should get 6.233 times 10 to the negative 5th rads per second. And remember, the formula that the kinematic formula we use here, if you know omega 0, omega, and alpha, you know time, you want time, but you don't care to have theta involved, it's going to be this. Omega equals omega 0 plus alpha t. That's what we're going to wind up using. But before we, and so now we know our omega, which is 6.233 times 10 to the negative 5th. Our omega 0 is 7.272 times 10 to the negative 5th. Plus alpha times t. We want to solve for time, obviously, because that's what it's asking for. How long must he push this force to accomplish his goal? But we don't know alpha just yet, so we're going to have to figure that out. Now, remember, torque equals your moment of inertia times alpha. Remember, torque is also your force times the radius. So we can actually make some sort of connection here. And actually, that's what I'm going to probably wind up doing to solve for time here. So let me go and erase some of the other stuff. So I'll need space, of course. Okay, so you can actually set those equal to each other. I times alpha. And the force, you know, is 4 times 10 to the 7th. The radius of the Earth we know is 6.38 times 10 to the 6. Now, we're dealing with a sphere, and it's a solid sphere that, the Earth is not thin. So we're going to be using this moment of inertia right there. Two-fifths times the mass of the Earth, which I know is going to be and then r squared. And again, you do have alpha as well. So I'll put the alpha right there. So we can solve for alpha in this fashion. So it's going to be a lot of calculator work if you're really, really careful here. If I do it carefully, so I have 4e7.
Mr. Amashni?
Yeah, go ahead.
How can you set I times alpha and force times radius?
Those are both torque.
Are they both equal torque?
Both equal torque. Yep.
Got it.
That's why.
Thank you.
So remember, the torque, we have a new equation for torque. That's from the second law of rotation. And we had one that we did earlier this week. Yeah, I'm just kind of just going through the motions here, just working all this out. So you divide by 5.98, E24, and divided by 6.38, E6 squared. Okay, so it's a pretty low value here. 2.621 times 10 to the negative 24 rads per second. Now, I made sure my units were all correct. I used meters for radius, kilograms for mass. Yeah, so that's what's happening there. The force is in newtons, so everything should work out just fine. In seconds squared, mind you. So make sure I've done all this correctly. Force, yeah, because then you get kilograms. Seconds squared. Yeah, I think should be okay. So now you're going to bring that back into this equation down here and solve for t. So alpha is going to be, and the one thing that we do have to be a little bit cautious about as well is that we don't want our time to be negative, because we are going to wind up getting a negative if it works out. And I'm looking at the solution key. It looks like they made the force negative. I guess because you're trying to go against the force that the Earth experiences when it rotates. So I suppose we should make that negative. So it's a negative acceleration he's applying, if that makes sense. But if I solve for this, well, let me keep that. So let me erase this here. So my time will be 6.233 times 10 to the negative fifth minus 7.272 times 10 to the negative fifth all over alpha, which I got is 2.62 times 10 to the negative 24. And that's rads per second squared. And the velocities are rads per second, so you're going to wind up getting seconds at the end. So we work all this out. So let me store this acceleration value. So you have 6.233 e negative 5 minus 7.272 e negative 5 divide by that. And it will take some time. And so I do get the answer the solution has here, so that's always a good thing. 3.964 times 10 to the 18th seconds. So that's how long it'll take this person to get the rotation of Earth to go from one revolution every 24 hours to one revolution every 28 hours. If you actually were curious how long that would be in hours or days or whatever, or years, it actually would be 1.26 times 10 to the 11th years. So it would take a long, long time for that to happen. But you can leave the answer in seconds, that's fine. So yeah, the key takeaways here is knowing the right kinematic equation. And then using this right here. And that did require a little bit of algebra and then bring it back in. So a little bit, go ahead.
I was saying like that was like really hard.
Yeah, it is. Yeah, it is. I think what I probably would do is I probably turn this into like several parts. I probably would say, hey, tell me what the torque is. Maybe your force, and here's the radius. So I think you guys could do that, right? That's not too hard. Then I'd say, tell me what the moment of inertia is. I give the formula. You can do that. And then I would say, okay, now you know what the torque is, you know what the moment of inertia is, find me this. I think you guys can do that. And then I would then I'd probably just explicitly tell you what the angular speeds are. I think this is just kind of just makes more tangible when you know one revolution for every 24 hours, but I probably may just give you the angular speeds right from the get-go. And then you use a kinematic equation as a result. It is multi-layer though. I think I probably would maybe make it a little bit easier than this, but the bottom line is, yeah, I would treat this as something that would do in multiple parts. Like, here's a force, here's a radius, give me a torque. Okay, now here's a shape we're dealing with, here's the mass and the radius, give me the inertia. Okay, now you can get, using another equation for torque is inertia times alpha. Tell me what alpha is, because you already solved for torque in the first part. I think that stuff should be fine. And then a kinematic equation after that. Here are the other values we know we got to solve for time. So I think I would design it as like a multi-step problem. Like here's A, B, C, D, E to kind of lead you to the answer. That is one issue with physics sometimes, that a lot of physics professors don't think to assess this way. I've been trying my best to assess that way with you guys, especially like the last one we've had in our last 3 tests. I kind of give you multiple parts. I think I might layer it a bit more on this upcoming test, so it's not as daunting. But this is stuff we can practice for sure tomorrow. So no worries there. Let's look at one more. But yes, to solve for the time and kind of see out, but you do need to think methodically here again. And I think I would give you that methodical. I would treat it. I would write it in such a way where I'm encouraging to be methodical. Like do all these different parts along the way. So let's look at one more here. Okay, so if your mind was blown, the last one, prepare to have your mind just explode. This next one here, a solid sphere. Okay, so you have the mass and the radius, and a thin spherical shell. Again, you have the mass and the radius. So same mass and radius, but obviously different types of solids. So different inertias they'll experience because different formulas for the inertias. Roll down a ramp that is 0.5 meters high. What is the velocity of each sphere as it reaches the bottom of the ramp? So we're going to have to be using conservation of energy. Remember conservation of energy, KEI plus PI equals KEF plus PF. So we know this, right? The only thing is that the KEI, you're gonna have to do KE rotation initial and KE translational initial. And likewise here. KE rotational final and KE translational final. So we will need to have to kind of go through all that. And we're going to be doing this for both the solid and the spherical and the thin shell. So we're actually going to be doing two separate ones. But this is the general concept is the conservation of energy. And again, for kinetic energy, we're not just doing 1/2 mv squared anymore. We also have to consider the rotational kinetic energy. So kinetic energy is actually, it's going to have two components here. Not just movement, like, you know, we've been dealing with like, you know, we deal with like this going down a ramp, right? But this box is not moving. But now what's happening is that you have this ball, which goes down this way, but it doesn't just go down, like let's say I have like a little marking here. It's not like the ball just does this the whole time, it rotates. So maybe this little marking is now here, and now this marking is down here, and now this marking is over here. Kind of like a bowling ball, right? Like a bowling ball, it's got those like 3 little holes, and you kind of see those holes kind of rotating, or a baseball, you see the seams rotating, or football, you know, you see that, basketball, lots of rotations going on there. So now that we know we're doing kinetic energy, conservation energy and kinetic energy can be broken down 2 ways. Let's actually calculate the velocity of each sphere for these 2 objects. So let's start with the solid sphere. And I'll do the thin over here. Kind of create a little division. Okay, let's get going here. So PI plus KE rot I plus KE trans I is equal to PF plus KE rot F plus KE trans F. Now right off the bat, I know this is going to be 0 because now you're at the bottom of the ramp. So you have no more potential energy. So that makes my life a little bit easier. Also, I know that these are going to be 0 because right now there's no motion, right? And I do know that this is MGH. We've talked about this many times. This right here is 1/2 mv squared. Sorry, I meant to do over here, 1/2 mv squared. Because that's translational. And this is going to be 1/2 I omega squared. Okay, so far, I hope you guys are with me. Okay, now you have the mass, which is 2 kilograms, gravity, which is 9.8, and the height, which I know is 0.5 meters, equals 1/2. Now it's a solid sphere, so we're going to have to be using 2m r squared over 5, so 2/5 times mass times r squared times omega squared, which is, we don't know what to do with that just yet, plus 1/2. The mass I know is 2 kilograms, and v squared, which obviously I want to find. Okay. We'll keep moving. So the left side, if I calculate that, 2 times 9.8 times 0.5, we'll get 9.8, easy peasy. 1/2 times 2/5 times the mass, which is 2, times its ratio is 0.25 squared. And now here's the thing with omega that you guys probably forgot. remember we talked about omega is actually going to be velocity over radius. So you might remember this from our notes the other day on 4.4. So yeah, it's kind of hard to see, but the velocity is r times omega, or omega is v over r. So you do have to use that also. So we do know that, so v is omega times r, omega is v over r. So we're going to do a substitution. So omega will be v over r squared. And these will just cancel. We get v squared. And let me make this a little more neat. That's r, by the way. They'll even neater. Okay. So we keep moving. Looks like some things will cancel out nicely. Those should cancel. If I keep moving, I get 9.8 equals 2 over 5, so you get 2/5 again. 0.25 squared, that's 1/4. So it actually becomes 1/16. Remember, 0.25 is 1/4. And I'm squaring it, so that's 1/16. Times v squared over r squared. So I'll square that again as well. And plus v squared. If you keep moving, 0.25 is 1/16 again, 0.25 squared. So you have 9.8 equals 2/5 times 1/16 times v squared. And you have another 1/16 on the bottom here as well. Because that's what so these are actually going to cancel out. So 9.8 equals 2/5 v squared plus v squared. 2/5 I know is 0.4. So 9.8 equals 1.4 v squared. We're almost home free. 9.8 divided by 1.4. Square root it. So you get 7 equals v squared. Remember, 2/5 is 0.4. And v would be the square root of 7. Or v is roughly 2.65 meters per second. So that's going to be the velocity it experiences when it gets to the bottom of the ramp. Now for the thin spherical shell, because it's hollow, I'm not going to expect to be having as fast of a speed as it heads downhill. So I'm going to have you guys calculate that one. And maybe what we could do is let's have you guys do this in groups. So you guys have this right here as a guide. Let me actually take a screenshot of this and email to everybody so you have it to look at. And then I'll put you guys in small groups. And now you're going to calculate the velocity for the thin sphere. And then we're going to talk about your answer after that. So let me take a snapshot. Okay. On. Okay. Close that down. And let's just clear it.
Stop sharing. Stop